as I was just saying, is unfortunately we don't have a lot of time left that there. We just can't afford to throw days away. So I'm going to proceed as if we have a full class. If people don't go back and watch the lectures, they will probably miss those questions on the final exam, and their overall grade will be affected right there. So I don't worry too much about attendance. I'll probably mark the gentleman absent too. And, I'll probably take attendance today just to be mean and nasty. So, all right, I'm going to jump ahead. We've been going through the Bride book, and the first couple of chapters out of the Bride book actually dealt with just basic information about the 8086, 8087, the history, where they come from, the makeup. This chapter here, I'm jumping to chapter 9, is the hardware. After I finish chapter 9 in this book, I'm going to be going to another book where I'm going to be talking the 8051. So essentially, when we look at this course and the final exam, what I'm going to be looking for is the first part of the class has just been general information. What is a microprocessor? What is a what it's used for, those types of things, the history of it a little bit. The second part of the final exam is going to be chapter 9, so this is probably at least 1 to 1.5 questions of the final exam is going to come out of this chapter. And then the last part of the final exam is going to be software, and that's going to come out of the other book. And the reason the software is going to be different than what we're using there is because the hardware we have is an 8051 microcontroller, so I will have some discussion on that there. So the last probably third of the course is going to be hopefully in the computer lab at least one day a week out there, and you'll be doing some labs right there. So, okay, with that said, I'm just going to jump in here. I'm not so sure how far I'm going to go today. Actually, I should have brought my coffee cup here to where I can actually drink coffee and lecture now, and my throat can be much clearer. The first part of this class, trying to teach that there, and with dry throats is hard. Okay, we're going to look at the various pins of the 8086, 8088. Now, again, these are obsolete processors right there, but the pins and the concepts are still the same. I think I mentioned I brought in a motherboard in class before Hari Raya got there. My most recent motherboard that I bought, which is an i5 microcontroller, which is a continuation of the 8086. Remember, this all started with the 8085 or 8080, and then the 8085 was the second generation 8080. Then the 8086 was the first 16-bit microprocessor. The 8088 was just a 16/8-bit microprocessor, and then the 186, the 286, the 386, the 486, the Pentium 1, the Pentium 2, the Pentium 3, Pentium 4, i5 first generation, i5 second generation, i3, i5, i7, and now we're on the sixth generation of the i5, i3, i7 out there. So these are all continuations. So all these pins that we're talking about on the 8086 and all these functions are just carried on with new, bigger, faster, more powerful processors that there. So it's like looking at a small motorbike. You can look at a Honda 125cc motorbike, or even a small Yamaha scooter out there, or you can look at a Harley Davidson 1200cc superbike, and they're still motorcycles that there. They still have the basic components right there. So same thing with microprocessors right there. So cars have not changed drastically in probably 75 years. The only thing that changed in cars has been the addition of electronics right there. Same thing with motorcycles. Microprocessors have changed quite a bit because they've gotten much larger and more powerful. They change faster than anything else. but the basic components have not changed that much there. So we're not going to get into these minimum mode and maximum mode operation. We're not going to worry about that simply because we are looking at a obsolete processor, one that you'll never use, and getting into the details of that particular processor is not necessary right there. So again, this just repeats what I said. These simple processors explained as introduction to the microprocessor. So the current i6, here our gentlemen are arriving at there, or at least one gentleman. The current i6 processor has 1,170 pins and 171 pins. The previous generation, the 5th generation, had 1,170. The processors we're going to be talking about has 40 pins. So obviously the reason we're going to talk about the 8086 versus the Skylake i7 processor is that, matter of fact, I was just reading an article, they now came out with a 10-core processor right there. So is that if we try to learn 1,171 pins or 1,170 pins, we would not be able to keep track of that there. And a lot of them are repeat pins, and a lot of them are buses that there. So we're going to be looking at the much simpler one right there. Okay, again, describe the function of each pin. I'm not going to require that you know the function of all 40 pins, but I can guarantee you that there will be at least a couple of questions on the final exam where I will list 5 or 6 pins and I will ask you what the function of those pins are. Those are very typical final exam questions right there. And not only will I ask you what the function is, but how to use them, those types of things, some basic wiring that they're. The DC characteristics, I'm not going to spend a lot of time on the DC characteristics, but you do need to understand what is meant by fan out and those types of discussions right there. And the use of buffers. We will not talk about the clock generator right there. We will completely forget that section that's there. And the reason we're going to skip that section is because most modern microcontrollers or processors have the clock generator built into the processor. They've sucked that into the processor right there. We will talk about buffers and latches to the various buses right there. Timing diagrams, we'll go through some of those. Those are the bread and butter of any digital engineer. And when I include digital engineers, I include embedded processors, I include microcontrollers, I include microprocessors, I include digital, advanced digital logic such as field programmable gate arrays, digital circuits. Everyone had basic digital, correct? Yeah, that there. Well, advanced digital, you go into custom logic that there, where you design circuits using Verilog or VHDL, and that there. Again, timing diagrams is how you troubleshoot and debug those things that there. So we're going to look at some basic ones. Unfortunately, we don't have a logic analyzer to spend time playing with that there, but we'll look at them at least in theory on what these timings should look like that there. Weight states, we're not going to talk about weight states right there. We're not going to talk about that. Okay, just kind of go through this right here. The 8086 is a 16-bit processor. It has a 16-bit data bus. The 8088 has an 8-bit data bus right there. Those pins are numbered right there. When we look at the 8086, you will see that there are pins that are labeled AD0 through AD15, and the 8088 has AD0 through A7 right there. Now, AD means it's address and data right there. So those are 16 of the pins on the 8086, that's 8 of the pins of the 8088, are the address and data bus right there. So the only difference between these two processors right there, and that's a key question, is if you're asked in a final exam question, what is the difference between the 8086 and the 8088, here's your answer right there. I can't give you a bigger hint. I just told you what the question is, and I've showed you the answer, is that the data bus width is the only difference between those two processors. They're exactly the same internally, right there. So, right there. The 8086 transfers data more efficiently. It does it 16 bits at a time. The 8088 has to transfer data 8 bits at a time. And it's kind of like driving, the federal highway, and you're going along, and it's 3 lanes on both sides, and then there's an accident, and now all of a sudden you're down to 1 lane out there. And some of you probably experienced that yesterday, right? Or over the weekend, out there. I was driving back from Malacca, I think it was Thursday, and it wasn't an accident, but there was a couple cars pulled off the side of the road, and everybody had to slow down and look at them. And that there, I use the phrase. Has anybody ever heard the term rubberneck? Rubbernecking is when you're going down the highway and you see an accident or something, and you have to turn, look, slow way down, and block traffic. So, and I find that living in Malaysia, that rubbernecking seems to be a favorite pastime on the highway, because there will be a 2 or 3 car accident going north on the north-south highway, for example, but the traffic is jammed for kilometer after kilometer going south. There's no accident or no road restriction, but everybody's slowing down to look at the accident, causing a jam on the other side. And of course, you got a jam going north from the accident itself. But regardless, you've got double the data bus size on the 8086 versus the 8088. Therefore, it's faster to move data in and out. So the bottleneck there turns out to be transferring the data in and out to memory. I mentioned this before. I'll remind you that the 8086 came out before the 8088. The 8086 is a slower processor, and the reason is at the time the 8086 came out, there was no 16-bit peripherals, memory chips, that there. So engineers preferred a processor that was only 8-bit simply because it was cheaper to build, that there, because you needed 2 of everything. You need 2 buffers, you need 2 memory chips, you need 2 ROM chips. You need to have twice as much out there. So building a motherboard around the 8086 was expensive at the time, or building a system around the 8086. So they went back to the lab, developed a 8-bit version, and they sold it for quite a while. IBM came out with the original IBM PC, which was the model 5150, which will not be on the desk. You don't need to remember that, but the original IBM PC released in 81, 82 by IBM used the 8088. Therefore, all the other copycat computer systems used the 8088. So the 8088 became an extremely popular processor for a number of years. It was probably the most popular processor, probably for 4 or 5 years. Right there. Even when the 8086 was more stabilized, people were hesitant to switch to it. When the 186 came out, it wasn't used very much, as I mentioned before, because the 286 was right on its heels, or just before it, right there. So the 286 was probably a good 5 years after the IBM PC. Before it became very popular. I remember buying a 286 system, I'm thinking 85. It might have been 86 when I bought a 286 system. But regardless, what the key point here is, the only difference is the data bus size right there. So, okay, these are the 2 right there. I'm only going to worry about one configuration or the other, and I'm only going to worry about certain pins. And I'm going to circle the pins that you're responsible in knowing what they do and how they do it. We'll talk about them. I've already mentioned those pins right there. That's 80 through 8015. The clock right there. The interrupt request, we'll talk about that. The non-matchable interrupt, we'll talk about this one here. The reset, I'll talk about that one there. The ALE, we'll talk about. The interrupt acknowledge I'll talk about. The memory I/O not I will talk about. These four here I will definitely talk about. And these four I will talk about. So as you look at it, we're going to talk about most of the pins. A few of them we're going to skip right there. We're not going to worry about the test. We're not going to worry about the min-max pin right there. We're not going to worry about the hold, the ready pin, those types of things there. We're not going to worry about. I'm not going to get too much onto the statics pins. The S, there's a number of pins that start with S3, S4, S5, S7. Right there, they don't bring out the S1, 2, 0, 1, and 2 right there, but those pins in the min mode, I'm not going to talk about those right there. So I'm just going to stick only on the min mode is what I'm going to be sticking with right there. So there are some extra functionalities in the max mode that there. Since this is an introduction to the microprocessor, I just want to keep it to the basics right there. So there. Okay, power supply. The 8086 required 5 volts right there, plus or minus 10%. It draws 360 milliamps at there. You don't have to memorize that there. The 5 volts you need to know. Now, I should point out that modern processors today are typically 3.3 volts right there. So So as we look at these processors, that the power supply voltage is a key, and when we look at the 8086, it's a 5 volt processor. The 8051 that we're using is a 3.3 volt processor. The original 8051 was a 5 volt processor. It doesn't really matter so much, other than you have to be aware of what processor is, and there are some interfacing problems you have to deal with if you're mixing that there. So I know I ran into some problems with the microcontroller board that I wanted to use it with the LCD for the interfacing class, and the LCD requires a 5 volt interface that there. So we ran into some issues out there. So, but again, but the only thing I'm so out there, this is from a U.S. book, so this is 0 Celsius and about 90, 80 degrees Celsius right there. Between 0 and 70, I think, is the standard operating range of most out there. There are processors out there that will operate in a wider range than that, and you might ask yourself why. This here actually is a very limiting factor if you live in a place like where I grew up. I grew up in central Minnesota, which is up in the northern part of the United States near the Canadian border, and we would see temperatures in the negative 40 range from time to time, right there. Obviously, if you've got a cell phone that's running on a microprocessor and it's sitting in your outside coat pocket and it's minus 40 outside, that cell phone's probably close to minus 40 right there. So this range is limiting. So they have extended that range that they're. And then I've also worked a number of years off and on with some military electronics, and military electronics, of course, has to operate in very extreme temperatures because, if it's in an aircraft, for example, it could be sitting there flying, at 40,000 feet up in the air or 15,000 meters up in the air, and it's cold up there. It is cold, and so if you've got electronics that are on the outside peripheral of the aircraft, they're probably close to minus 100 degrees Celsius. It's pretty cold up there, not quite that cold, maybe minus 50, 60 degrees Celsius. But if they're near the jet engines, they may be up to around 150, 170 degrees Celsius. So temperature ranges of electronics is an important factor out there. Not so much for consumer electronics out there. The differences, things say for an automobile ignition system, it has to operate at minus 40 when you try to start the automobile in Minneapolis, Minnesota. And it also has to operate in Kuala Lumpur, Malaysia when you're going down the drive around KL in a traffic jam and the temperature outside is 45, or 35, but under the hood of the car in the sun, it might be plus 55 or 60 out there. So, temperature ranges are important. They really are out there. Because a lot of people look at this and go, well, that's plenty good. Any computer I'm operating is going to be between those two ranges. Not too many people are going to sit in a room that's 0 degrees Celsius and sit there and try to use their computer. But I have watched many people out in the field doing surveying, for example, in the construction crew, when it's minus 20 degrees, trying to use their surveying equipment. I've watched many people try to start their cars at minus 30 degrees and want them to start. So these ranges do make a big difference at their in extremes. In the opposite end, 180, that's about, as I said, around 70, 75 Celsius, that range there. It never gets that hot in KL, fortunately, out there. We would be pretty well dying. Your oven is set to that temperature if it was that there. But inside the passenger compartment of your car with the windows closed, with black seats out in the sun, you might be coming close to that 180 Fahrenheit degrees. That's getting pretty warm out there. That's one of the reasons why you don't leave children in cars right out there. And I know it's happened here. It's happened in the U.S. Places where somebody wants to run into the store for a short minute, and they leave their baby sitting in the car seat, in the car taking a nap, and they're in the store longer than they expect to be, or get hung up, or and they come back and the child has died in the car. That has happened more times than we care to think about, and that's because inside of a vehicle with the engine turned off and windows rolled up, it can get very hot. So that's kind of a side note. It's not part of the chapter, but as I mentioned, temperature ranges. Temperature ranges are important. These are some low power out there, and notice here, these particular processors, the range is, and minus 40 Fahrenheit is the same as minus Celsius. Is minus 40 Celsius. That's where the two cross right there. Plus 225 Fahrenheit is about 105, 110 Celsius. So, so there are, they come up with processors that will operate outside that range right there. And to be honest, I didn't look at these slides ahead of time to know that this next slide covered these wider range. But the reason I went through this is because I wanted to point out that your selection of processors has to take into consideration the temperature range. This next bullet point shows that there are processors designed to operate in these wider ranges right there. And they also draw a whole lot less current, but they're also a lot slower right there. You give up something. You're only going to run 10 milliamps of power, and you can operate in a huge range, but you're going to operate at a fraction of the speed right there. And right there. Okay, DC characteristics, you have to be aware of anything, and this is not true on just microprocessors right there. Anytime you have a microprocessor pin or a pin to any digital device right there, I don't care what it is, it's digital. It could be TTL, it could be CMOS, it could be MMOS, right there. It can be any type of digital logic right there. It doesn't matter. It's going to draw some current in right there. It's going to have so much current going into it right there. And anytime you have an output pin, it can draw so much current out right there. The amount of current that you can source is important, because if you try to draw too much current, you're going to burn up the chip. Here, if you're drawing too much current, you have to be aware of there. So the amount of current in, the current out going into a digital IC is important. We typically ignore that on the design standpoint, but at some point before you go to the final implementation, you have to check your what they call your fan in and fan out. You know, fan out is how many loads, number of loads, right there. You know, how many devices are connected to that there. Now, if you take, for example, a device such as a pin such as AD0, for instance, it could be tied to 20 different loads right there. And when I say 20 different loads, every memory device, every address decoder is going to be tied to this bus right there. So when we tie a lot of things to the bus, we have to put buffers on there in order to ensure that we don't draw too much current coming out right there. And we also have to look at what's going into this, because that's a certain amount of current, because that's going to determine whether or not that's there. If we're driving, for example, a load such as a DC motor, obviously a DC motor might take 50, 60 milliamps right there. We're going to have to put that through some kind of buffer or some type of driver or some type of circuit. So we have to deal with these DC loads as far as current goes out there. So you have to be aware of this fact. We're not going to spend a lot of time on that there, but it's something you do need to be aware of. And the term fan out is the number of loads you're going to be driving. Then the fan in or current in is out there. And you have to do a basic check on your final design before you release it or build it in the lab. Make sure you're not going to burn something up by drawing too much current out there. So you just out there. Another thing to keep in mind out there is that as we draw current, we're reducing the resistance out there, and we may be affecting the timing out there. When we look at my pen, this thing's not quite 2 years old. Probably time for a new battery again. The batteries run out about every 3 to 6 months on this thing here. Right there. Yeah. Oh, that's working. You know what? I bet you I'm not going to worry too much about that. Let me just kind of point out that every time you have a wire going from point A to point B, and this could be a wire, it could be a trace on a printed circuit board, most likely it's a trace out there. You've got capacitance between that and ground and other wires right there. And as you draw current through here, you've got that there, and it's going to affect how rapidly, that there. If you have a signal that goes like this, what gets to the next point may be something that looks like this right here. You have this stray capacitance and this resistance of the wire itself right there. And when we look at this right here, that affects the amount of timing, because this is going from low to high, but it doesn't register a high till it reaches this point. When it goes from low to high, it doesn't register a low till it reaches that point right there. So the time from here to here is the amount of time it takes for the signal to propagate onto the next level right there. So as we look at these DC characteristics, it's going to affect our timing. How fast can we run our system right there? Because in a perfect world, we could run everything at 200,000 gigabytes or gigahertz right there. We can run our processors so fast that we don't need to make bigger processors. We just crank up the speed, just like you see the people on the federal highway get on their motorbikes. They just turn that throttle up to make it go faster, right? Well, they reach a point, the thing's not going to go any faster because the engine's going to, the friction, the motor, the friction of the tires is going to slow them down out there. You have a speed limit out there. And what normally slows us down with microprocessors are these DC characteristics as far as timing goes, right there. The RC time constants there. And it used to be internal to the microprocessor itself, they call it the size of the transistors inside, that the bigger they were, the slower they would operate. Now those things are down in the sub-micron range. They're so tiny, so tiny. There's so many billions and billions of transistors on a single microprocessor out there. But as soon as you go off that chip, everything slows down. And it gets even much, much slower when you get off the chip and farther away from it on the motherboard or onto another board, such as a memory module or a video board or something like that. So you have to be aware of this DC timing situation out there. So again, it's knowledge that you have to have. We're not going to cover it in great detail because we have an 8-week class, 7-week class to teach you everything you need to know about microprocessors to be dangerous enough to blow up something right there. You're not, in other words, after this class, I would not put any of you in a microprocessor design unit and say, let's start designing digital systems. But again, you at least, I would put you in the unit and say, all right, put you in that department and say in 6 months you should be able to start learning how to design systems. But you're not going to be designing systems from day one, so we're not going to get into that level of detail right now. Input characteristics, again, and where's our tables? Our tables are down here, right there. The tables are in the book, unfortunately, and I don't have the book. I can bring the book up here. But again, here we're looking at a typical 5-volt. Their input current levels are very small. All we're looking at is that our voltages on the 8051 are 5 volts right there. A general rule, I shut one node off and I should not have done that. Now my computer's it's copied stuff. All right. Yeah, it's not going to. Oh, here we go. Yeah, it's not going to bring it up. Okay, well, I guess I'll have to live with what I've got here then. Okay. At their basic characteristics, I'm going to skip through that there. Again, the key thing is that when we look at there, I'm just going to write them down here. A zero. Oh, now I've got all kinds of issues going on here. Now my pen's not wanting to work. Time to stop and buy another 4A pin. They're a pain to get. There. Most people haven't even heard of you know what a double A is, right? There used to be an A battery out there, and they haven't sold it in probably 30, 40 years. I remember the A battery, which was a little bit smaller than and there was a B battery actually too out there. So the B battery was a little smaller than the C battery. The D battery is the great big one. C battery is a little smaller one. The B battery was somewhere in between. The A battery is somewhere in between. Then the AA that there. Now the triple A's is standard. Now they've got the 4A's out there. But getting back to here, 0 volts to 0.4 volts is 0 right there. Anything 2.7 volts to 5 volts is a 1. That's the standard digital logic that there. Anything between 0.4 and 2.7 is considered unknown. You should never operate in that range. But those levels have changed greatly over the years because 2.7 has actually dropped down to about 1.5 because you're dealing with 3.3 volts systems right there. So right there. So again, you're looking at 0.7. Actually, this one here says standard logic has a maximum voltage that there. A lot of standard TTL they use 0.8 or 0.7 is anything below that's a zero. But that there. So we talk about noise immunity. You try to keep things down in that zero rate. There. The larger the range you have, the more noise immunity. And noise immunity means that if you have noise on the board or in the line, it's mistaken for the wrong signal. And that's why 2.7 is considered fairly high up there. Anything below 2.7 is supposed to be down or viewed as a zero. But I'm not going to worry too much about these levels. Don't get hung up on these levels up there. This is a key thing to keep in mind, though, right here, right there. If there's, the only thing I'm going to really hit on is how many loads is too many. If I have more than 10 loads of any type connected to an output pin, I need to buffer it. That's just a general rule of thumb. That there, and again, if you exceed this, noise will begin to take its toll on the timing problems. You start ending up with timing issues. You start ending up with, brownouts where signals are lost because of the noise that there. We end up with too many losses on the what I want to call the IR drops. As you're drawing current through the wire, there's a voltage drop across that wire or that bus. So this is a rule of thumb. It's not cast in stone. Some loads you can't have more than one or two loads. Some loads you can't have any. You have to buffer right away. Some you can put up to 20, 30, 50 of them, depending on that there. But again, it's just typically they say that you want 10 loads is the max out there for standard TTL. Okay, now we're getting into the highlights here of this chapter. We have here, this is talking the 8088. We can extend this to the 8086 by just simply changing this word to a 16 right there. Right there. There's that there contains actually all 16 bits of the or the uprightmost 16 bits of the address right there and all the data bus. These lines are multiplex. When they mean multiplex, means that sometimes you're one thing, other times you're something else, right there. So, just like your phone is sometimes a phone, sometimes it's a computer, sometimes it's a music player, it serves as a multi-purpose device, right there. Most cell phones you can watch movies on them, you can play games on them, you can listen to music. So it's a multiplex device. It can do 3 or 4 or 5 different things, not at the same time, effectively. Now, a lot of people think that they're very effective at doing 2 things at the same time. I beg the different as I watch people try to drive a motorcycle and text. It doesn't work very well out there. As I've seen people drop their cell phones trying to answer them as they're going down the road on their scooters. You should concentrate on one thing at a time. And the address and data bus can only be either a memory or an address bus or a data bus. There's a line called the ALE. That was one of the lines that I circled. That there in that line is the address latch enabled. When that line is low, it's a data bus. When that line is high, it's an address bus. That's simple, right there. There's 3 points on your final exam, if you can remember that, right there. Right there. Is the address bus that there is either it's data, if the ALE is low, it's an address bus if the ALE is high, right there. So, right there. Right there. Now, if there's an acknowledge, which I said we're going to skip the acknowledge state, it can also go into a tri-state mode. Right there. But again, I'm not going to hold you up there. Right there. The A15 through A8, or this is only on the 8088. This is the provides the other. It's not quite the full upper half of the address bus. There's a mistake there. The 8086 has address lines A0 through A19. There's 19 address lines on the 8086, 8088. That there. 4 of them we'll talk about here in a minute. That there, and those are tied to the status bits there. But on the 8088, the upper 8 bits, or A15 through A8, are not multiplexed. They're just address bits all the time. So we don't save any pins out there. The reason we do this is that we want to save pins. Now, as I mentioned before, modern processors have almost 1,200 pins. They don't bother multiplexing because multiplexing means that you have to slow down to put the address out first, latch it, then put the data out separately out there. So it requires additional bus cycles. Modern processors, they've just put more and more pins on there. They made the chips bigger and bigger and bigger. Actually, they're not very big. I took the one out the other day, and you saw even with 400 pins, it's still not much bigger than these old 40-pin devices that do. But the key thing is that those 8 lines are not multiplex out there. So go that there again, same thing. They go to a tri-state. That there, and again, these are all the multiplex. So AD0 through AD15 are pretty much all the same on the 8080s or on the 8086. On the 8088, you've got AD0 through 87 and A8 through A15 at there. That there. So contain address bits A8 right there. Again, looking at the ALE right there. So they operate the same right there. And these are the other 4. Our multiplexer provide the address signals and the status bits right there. So again, these are telling the debug hardware, which we're not going to get into, what's going on inside the processor. That's why they're called status bits. We would normally not use those bits in our design, but they're used in debugging our processor. We have a different way of debugging today, and you'll see that there. The debugging tools we have today are vastly superior than what was used back in the 1980s when this whole concept was come up with there. That was 81. You're talking 40 plus years ago. I mean, there. Now we use something called JTAG debugging, and you'll see that when we get it in the 8051 how that works out there. So, but we have these lines here that are multiplex. One important thing that's not covered in the slide, it may be on the next bullet, but the ALE is equal to 1 whenever these are address lines. So we can use the same ALE to demultiplex those lines up there. So, at there. So, again, status bits can address 4 different memory by decoding that there again which segment is being that there. Again, you can look at some of the memory right there by decoding that there. So that there. Again, I don't want to get into the status. So what we've got here is we've got 20 address lines and either 8 or 16 data lines, depending on which processor we have. The 8088 has 8 data lines. The 8086 has 16 data lines. As we get into newer generations of this processor, we could get up to, say, the 6th generation i7 that has 64 data lines. you can see why it's needing so many pins right there. And it has 32 address lines. I mean, we're up over 100 pins in just address and data lines right there. We're close to 100 pins, but you're at 96. So as these processors get bigger and bigger and we stop multiplexing the lines, we need more and more pins right there. So, right there. The ready that there inserts wait states in the timing. We're not going to worry too much at there. Enters wait states and remains idle. The ready line, and you can turn off your brain here if you want. I'm not going to put it on the final exam. The ready line was used back in a day when memory was slow enough that we had to stop the processor and let the memory catch up right there. Or we were using coprocessors or something called direct memory access right there. And let me just kind of mention this term, direct memory access, and that is basically when we do direct memory access means, and I'm going to probably have to erase this. Here's our CPU, and here's our memory right here. Normally, these are our address lines, these are our data lines, and these are our control lines. And we'll look at these various buses later on. And the only thing that talks to memory is the CPU. That's in a normal microprocessor, microcontroller operation. The only thing that ever talks to memory is the CPU. There are designs in our situations that we sometimes want to bypass the CPU and go directly from memory to memory right there. An example of that might be is I've got a graphical GPU, graphical processing unit right there. And that's very common with today's high-speed graphics where you want to do video games, 3D graphics, and those types of things. We have another processor that does graphics right there. We have a CPU that is our general purpose microprocessor, and we have memory that we share between the two of them. So we want to load a bunch of memory into here, and then we want to take it from here and put it there. And we want to do it so fast that we don't want the processor to get in the way. So we tell this thing to go to sleep for a few minutes, and this will access our memory directly right there. It's not, that's an advanced subject that's really beyond the scope of this class. I've used DMA for accessing a lot of the early hard drives, because if I want to load a bunch of data from the hard drive to memory, it's quicker to have the hard drive controller talk to the memory directly and not go through the CPU. So you would put the memory to sleep right there. So it's one of those types of things that we used it, it's talked about because it was a very common thing back in the 1980s, even into the 90s. With so many pins available and the speeds that these processors operating with, we typically don't do it much anymore. But again, so we got that there. When a read signal is receptive, when we take it high, it goes there, and we have the ready line that there. Okay, 2 pins that I will put on the final exam, right there. And let me talk a little bit about an interrupt there first. There. And what an interrupt is, and I'll just do this verbally. Right there. How am I on time? Oh, right there. Okay, what an interrupt is you tell the processor to stop doing whatever it's doing and surface something else. The easiest definite explanation I use is, and I'll pick up on the ladies here because it's typically ladies that are nurses, although in the U.S. we have a lot of men that have gone into the nursing profession. That's there. But a nurse working in a hospital, I'm not talking about the one in your doctor's office, but the one at the hospital that's working the 3 a.m. shift, the one that starts work at 11 o'clock at night and is there until 7 in the morning. That there, when things are quiet, that there, they basically do odd jobs. The American nurses, and I'll use the American example. I have an ex-wife that's a nurse that there. I put her through nursing school, so I know exactly what she did. I used to bring dinner to her as she worked the 7 p.m. to 7 a.m. shift, so I know what nurses are doing at 2, 3 in the morning because I'm showing up at the hospital bringing dinner up for a number of them out there. And most of the time they're sitting there reading books, chit-chatting with each other, maybe watching something on the TV, surfing their Facebook pages, checking their phones, but they're not working real hard. They have 4 or 5 patients assigned to each nurse. Once every hour or so, they go around and they make their rounds. That they're to check on each of the patients. However, each patient in the room, and I got to spend a lovely 3 or 4 days of my life at Columbia Asia Hospital over on Stoppock about a month ago. That there, and it's very much the same thing. That there, I wandered out from my room at 2, 3 in the morning, and I saw all, everyone's just sitting there chit-chatting around the nurse's stand, that type of thing. But there, actually, I spent 2 days in ICU, and then they had. One time they had 2 nurses assigned just to watch me. I was the only one there in ICU, but they had 2 nurses and out there, and I wasn't that bad. I could get up and go to the washroom and stuff by myself, but they had to. Every time I had to go to the washroom, they had to disconnect all the monitoring equipment. But regardless, that every room is equipped with a little push button to call the nurse. Depending on the patient, they may have a heart monitor on them, they may have a breathing monitor, they may have all kinds of various equipments with alarms on that there. They may have a piece of equipment for infusing fluids into that there. I had one of those because I was getting some pain medication. I'd gone through some minor surgery out there. Obviously, you see me walking around, it wasn't major. I lived through it out there. But regardless, that there, use an example. I've got an IV pump, and it's pumping in saline solution or that there, which is basically salt water. And every time I'm in pain, the nurse will come by and give me a little, I think it was tramadol they were giving to me through the IV that there. But this machine would run out, that there, and whenever it ran out, it would sound an alarm. Well, the alarm was loud enough that the nurse sitting across the hall that there, and this was in the ICU where I had the IV, would look up, walk over, and change the bag, or turn off the machine, depending on whether or not that's there. Well, that alarm is the interrupt. That's there. So, with the microprocessor system, right there, we have these interrupt requests. It's used to request a hardware interrupt, right there. Another type of interrupt might be my heart rate monitor all of a sudden goes beep. You see those on the movies, right? Hopefully nobody's ever seen those in real life. That there. So I've seen a few of them in real life that there go off, but that basically means the patient's heart would stop. Well, these are 2 different types of interrupts, right there. So if an interrupt occurs, the processor will acknowledge the interrupt and complete its current instruction, right there. And it goes through a series of steps, which we'll go into more detail in the second half of this course. Because we'll be looking at programming interrupts and how interrupts occur, and how we would set up interrupts. But we would have these interrupts occur, and normally we would do what we call an interrupt service routine upon the interrupt. The interrupt service routine is dependent on what type of interrupt it is. With the 8086, there's one pin here called the interrupt request, in which case, when that happens, an interrupt has occurred, the microprocessor would go out and ask the interrupt controller what interrupt occurred. With the 8051, which is what we'll look at in more detail, then the pin itself will tell us what interrupt it is right there. But we would then go and service the interrupt. obviously the interrupt request routine or the subroutine or the program that I'm going to run, and this is a program that I'm going to run, is different if a patient's heart is stopped beating than if their IV solution bag is gone empty. You would do two different things. One, you would walk over, pop out the bag, hang a new bag, and restart the machine. The other one, you would probably call some doctors and start jumping on the guy beating on his chest. That there, maybe put some paddles in there and jump start them like you would like your car in the winter in Minnesota. That there, but you would do something different than change a bag. So every interrupt has a particular set of events that occur. Now, I'm using the nurse for example. Hardware-wise, you have a gasoline pump that's pumping petrol. An interrupt might very well be that the pump senses that the tank is full, so it shuts it off. Or it may indicate no pressure, which means that the hose is broken, and you probably should shut it off. Or it may sense that the tank is empty and there's no more petrol in the tank in the ground. Those are, again, interrupt events that occur right there. So interrupts can occur in all kinds of places. While I'm talking about interrupts, there's also something called polling. Now, polling means that I'm not relying on interrupts. I'm going around checking all the time. That's the opposite of an interrupt, in that the nurse, when she gets up from her station once an hour or once every 30 minutes or whatever the protocol is, and walks around and sticks her head in each of the rooms that there, sees whether the patient's still breathing, that's polling. She's doing her rounds and checking. A security guard, for example, in a building, may walk around the mall once an hour and check to make sure all the doors are locked. But at the same time, there's alarms on each of the doors. So if somebody opens the door, the alarm goes off. That's an interrupt. So you have either polling or interrupts. Interrupts is like an alarm. A polling is where you're going through and you're physically checking each activity out there. So you'll get into those interrupts, and we'll talk about those in more detail. But there's a pin called interrupt request. There's also another pin called interrupt acknowledge, which is not listed right there. Another pin, which is similar, is called a non-maskable interrupt. One of the things that happens that there is that there's an interrupt flag, which basically means that I can disable my interrupts. I can ignore the interrupts right there. A non-maskable interrupt is one that I cannot ignore. I have to process it there. The bag that's sending the beeper sound, I just walk over, just shut the arm off and walk away and not do anything with it. I don't have to change the bag. I don't have to, turn off the pump or anything, remove the IV. I can just ignore it. Just silence the alarm and ignore it. You're on a flight from Kuala Lumpur to Sydney, Australia. It's a 7-hour flight, 8-hour flight, and you hit the little stewardess call. You want another bag of peanuts and another Pepsi or something right there. So the stewardess doesn't have time for you, so she walks by, turns off the light and ignores you and goes on by. That's that there. Or if you're not a Muslim and you're on your 4th beer and she's not going to give you a 5th beer, then they'll ignore the interrupt out there. But on the other hand, on the flip side of it is if you're about ready to throw up all over the front seat of the plane because you're suffering from air sickness, you probably shouldn't ignore that. That there. So you have different levels of interrupts that you can mask and ignore, others you can't. Right there. That there. So the test I'm going to just ignore. That there. The clock, right there. First off, there's the reset pin. The reset, right there, basically takes the microprocessor into a reset state. That there. It has to be held high in this particular case for 4 clock cycles. Most resets are, by the way, active low. This is an unusual processor. They've discovered after this that it's better to have active low. It makes designing the hardware easier. This particular processor used a clock manager right there, so it's as a result, the clock manager handled the reset. But most microprocessors have done away with that they're using active flow. One of the things that happens it's important is that there's a start address. Resets that it starts at address FFFF0. That's a starting address that there, and obviously you've only got 16 bytes of address there, so that's usually a jump to main or not there. It's usually a jump that there. But when we look at our processor that we're going to be doing software with, it's going to reset to 0000 right there. Reset there. But you have to look at where the starting is, and that's where you write your starting code from. Normally, your compiler or your assembler takes care of that for you. The clock pin provides that all processors have to have a clock. We will discover that when we look at the processor we're going to use in the lab, it has the clock built into the chip. You don't need an external clock right there. The 8086 required an external clock right there. And it had to be a fairly complex clock right there. This particular clock had to have a duty cycle of 33% to provide the clock proper timing. Everything must be grounded. Every device in a hardware system must be shared to the same ground. If I connect two pieces of equipment that are physically separated from each other, they must share a ground between them. Example, a USB thumb drive you plug into your PC. One of the pins on that is a ground right there. They don't necessarily have to serve the same power. I can have an external device operating on 5 volts, and I can have a microcontroller operating on 3.3 volts, and they can talk to each other perfectly fine. They don't have to share the same power, but they have to share the same ground. The ground is your reference point. Everything must share the same ground when we look at digital electronics microprocessors. Everything. And ideally, everything is tied to a physical earth ground out there. Now, I've had problems with houses, especially in rural Malaysia. I used to live in Kelang 20 years ago, and their grounds were very, very uncommon in houses. They just kind of let them float, and I discovered that I had all kinds of problems with lightning and taking out modems and things like that until I hooked up a wire to my computer case and stuck a 2-foot steel pipe into the ground with a wire attached to it. Right there. So ground, the term ground literally means it's tied to the dirt outside. Right there. That there, an ideal case. I think I'm going to stop. I noticed one of you is dozing off that there. So, that there. How many people were driving late last night? Yeah, we're still at right about my hour talking that there.